You're seeing over here is a more or less traditional way of having a client-side software which is relatively thin, and most of the stuff is actually happening on the server. How many of you are, I have to ask this question precisely, how many of you are aware of the fact that you're often using the X system? I have to think about this one. Very good, okay. Actually many of us are using something at least very similar to the X system if you, for example, already use your Android smartphones. But let me explain briefly what this is. And the interesting thing, or maybe confusing thing about the X system, it's a user interface where the notion of client and server have seemingly been reversed. But it is actually correct. They've reversed it correctly. What you're seeing here is the following. Last time I talked about that you could have, let's say, user interfaces, application servers, and database servers. Now in the X system, what you do is on the user's terminal, you actually run a piece of software, okay? And you have a bunch of application servers that talk to your screen. It's not really your screen, it's your device that you're using as an interface to the distributed system. If you take a look at the definition of client-server computing, what you will then notice is that these applications are actually talking to your device, that is your interface, as if it were a server. Your applications have become clients of your machine. That's the reason why in the X system, the notion of client and server have been reversed. And strictly speaking, this is correct. Okay? And to add a bit to this confusion, you as a user are accessing applications, and you as a user are a client for those applications, but those applications specifically are clients to your machine, to your interface. Okay. What actually happens is that these applications, they request the terminal to move certain things like the mouse and stuff like that on the screen. And they do this by means of the so-called X protocol, which is just an application level protocol that lets applications talk to your machine. Now this is a very natural way and common way of building an interface as an access to a distributed system, and the interface of course resides on the client, okay, on the client machine. Technically, software technically, the applications are clients of a server, which is a screen server, you could say, running on your machine. Okay? Yes?
How do the client applications send messages to the server? Is that through sockets?
In the end, yes, through sockets. Okay? It's just ordinary communication. What? Oh! How do clients, thank you very much, how do applications actually communicate with this client machine? Yes, through ordinary socket programming. Okay, keep me awake, okay? Is this scheme clear to everyone? Okay, let's move on to the next one. This is actually much more important. If you take a look at distributed systems and you take a look at real client-side software that sits on the client machine, has nothing to do with interfaces, what you'll notice is that there will be software that tries to realize these distribution transparencies. And one important one is, of course, access transparencies. And although I haven't explained what remote procedure calls are, basically what it boils down to is that you have software that is automatically installed on your machine that will allow you to have remote access to other parts of the distributed system, such that the application which runs on your client machine is unaware of the nitty-gritty details of how that data is actually being accessed. That's typically client-side software. You often also see location and migration transparency software. Basically what it boils down to is that the software is installed and running on your machine that keeps track of where data actually is. Now there's a subtle thing over here. In many cases what could also happen is that your client machine first contacts a so-called proxy server, and that proxy server keeps track of where, for example, your mobile data is. The essence is exactly the same thing. Okay, it doesn't really matter that your machine accesses the proxy server or that that software is actually running on your same machine. Okay? You also see replication transparency. This is something that I discussed last time, I think it was, when I was talking about how you can intervene in the flow of control in middleware, and you can place request level interceptors that will allow an application to not see the fact that a service, or server I should say, has actually been replicated. And what happens with the request level interceptor is that your call to that server is replicated to, let's say, the 3 machines where that service has been replicated to. One that, if you think about, can only be implemented on the client side is software that realizes failure transparency. Okay? Just imagine that the software that is needed to hide the fact that failures may happen and that you can recover from failures would be placed only and exclusively on the server side. Won't work, right? Why not? If the server fails, then hey, you can't hide it anymore. So the only thing you can do is you actually place this stuff on your client machine. And what you'll notice is that bare client-side software for distributed systems actually concentrates on failure transparency and most notably also access transparency, those two. Okay? So I think that's kind of clear. This is the easy part of distributed systems. Let's take a look at servers. How many of you are actually running servers at home? Very good. Okay. Why aren't the rest running servers at home? Exactly. Thou shalt run servers at home. In its simplest case, you have servers that run as ordinary internet servers, and then unfortunately nowadays many of these things actually happen completely automatically. But if you wanted to go into the fun part, you configure these servers, and what you start to do is you configure ports. Yes, that also means fiddling with your NAT firewall because you have to open ports. I would advise you not to open all ports. That is really a bad idea. Okay? But the crux of the matter is, when you are running a server, whether it's behind a firewall, that really doesn't matter. If you're running a server, the bottom line is that in order to talk to that service, you have to follow a protocol. And most of the servers that will encounter are kind of standard services that talk according to a specific protocol, and that protocol has an associated port number. And here you have a list of traditional ports. These things have been here since the beginning of the internet. So many of you are probably not using FTP anymore, or if you're using it, you're using it under the hood, and you have 2 ports for that, a data port and a control port. Some of you who have been taking a class or a course on computer networks knows that FTP has 2 channels, one for transferring the actual files, and there's one other TCP channel for actually sending commands back and forth between the server and the client. I hope none of you are using Telnet. Good, because my next question would be, I hope lots of you are using Telnet or have used Telnet, but the latter remark is actually with respect to the following. How many of you have ever opened a Telnet session to port 80 of a web server? Thank you very much. Then you know what happens, okay? So you can use Telnet to actually discover how an application level protocol actually works. Telnet is so simplistic, and you just have to start executing, for example, in the case of HTTP, actual HTTP commands, and then you will actually see over the screen what is happening. Okay? It's a pain actually because you can't make a single mistake, but you actually can make this protocol work manually. It's kind of fun. One that's, I don't care about the rest. But most of these are kind of pre-assigned ports, and there are some very old ones, Sun RPC, Courier, that's a Xerox RPC protocol. I don't even know for sure if it's still running. Probably it is, but not in great quantities. Okay. When you build servers, you can do this in very different ways. One that is still used, I should say, in many Unix systems, and I guess also in Windows systems, is the notion of a super server. In Unix, it's called the INetD, the Internet Daemon. Basically, it's a process that listens to many different ports. Okay? So it's a proxy to many other servers. And as soon as it gets a request for a specific service, meaning it gets a message to one specific port, it spawns a process that actually implements that protocol. INetD was originally installed because managing the resources on a service, resources on a service were generally scarce, okay? So if you would just have this super server sit in place and then spawn processes as needed, the idea would be that you would save on resources. By now, you still have INetD, but resources for certainly the standard services are not scarce at all, and you just simply spawn a bunch of processes from the start. I gave the example of Apache last time. If you start Apache, you actually start, I think, about 10, by default, about 10 Apache processes. Okay? Nobody really cares anymore. One thing that is important are iterative versus concurrent servers. Okay? Most of us actually build concurrent servers. But there are still lots of iterative servers floating around. An iterative server is a server that can handle, in principle, only one client at a time. It's very much like I discussed last time. You build a server as one big finite state machine. Again, from a software engineering point of view, or simply from a maintenance point of view, it's much easier just to have a bunch of servers collaborate when they actually develop a service. Apache is, again, a very good example. I'll just put on the whole slide at once. It's very important to have facilities to communicate with a server while it's doing stuff. The canonical example is, hey, you just launched a request for pumping a gigabyte of data to or from a service, and you just discovered that you made a mistake. You would like to tell the server that you just made a mistake. Okay? And there are essentially two ways of doing this. You can use a separate port for urgent data. Basically what it means is that you have your service or server up and running, listening to two ports, at least two ports at the same time. One is, again, for the regular service, and another port is being used for sending very specific control commands to that server. What you will need from the operating system is that it allows to prioritize ports. Okay, at least I should say preferably, because it's not strictly necessary. What is at least necessary is that the operating system will round robin when it's listening to ports. Because when you send a command to this special port like, hi server, I just did something terribly wrong, you do want to have that control picked up before this huge gigabyte file is actually transferred over the internet, because then it's really too late. Okay? That's called out-of-band communication. Out-of-band because you're having a separate control channel parallel to the channel that you're using for normal operation of the service. You can also have in-band communication, and this is essentially what TCP supports. Now, many of you may know that TCP has this urgent pointer facility. You can set a bit in the header of TCP packets, or segments I should say, saying that, hey, I'm now sending you a packet, and it's actually a control packet that tells you that you should pick up what I'm pointing to. And the urgent pointer actually points to a handle that describes what the server should do. Okay? It's very common to use both, either scheme. I'm not in favor of using one or the other. If you don't have separate ports, you use the TCP urgent pointer, and otherwise you just use separate ports. But what I'm trying to say is it's important to have communication with the server while it's doing stuff for you. That's part of the design of a server. Okay?
Could you give an example of a protocol that uses TCP urgent messages?
As far as I know, okay, I wanted to say you can break off a TCP connection, but that's actually already part of the TCP protocol. No, I used to have an example, but I can't come up with it. Maybe somebody else has an example where you actually use the urgent pointer in TCP?
Maybe FTP actually uses two. There are two versions of FTP, right? One with the 2 ports and one with the 1 port. It's fast.
There are two versions of FTP. I have to repeat you. I was instructed.
Fast and active FTP.
An FTP? I don't know. It could be. If you have the 1 port version with FTP,
Passive.
the passive one,
I'm
then
not sure if it uses the pointer, but
I don't know either. Okay?
it uses just 1 port.
What you would normally do, let's face it, if you're building a normal service and you wanted to do it the right way, I would argue that the right way is that you listen to multiple ports. It's just much cleaner to have a separation between, let's say, a control channel and a data channel, like standard in FTP. And I have some examples of the urgent pointer in TCP, but they don't pop up at the moment. Okay? Yes?
Could an example be like if you request a web page and you cancel?
Well, so would an example be that you request a web page and you cancel it? In many cases, HTTP is generally built on top of TCP, and when you cancel an HTTP request, what you're actually doing is, in many cases, you break off the TCP connection. That is already part of the TCP protocol, and what will happen is that both sides will come to the conclusion that the TCP connection doesn't work anymore, and then take action from that. Okay? While talking about this, an interesting experiment that you may want to check out, write a very simple piece of code that sets up a number of TCP connections and instantly also tears them down. Okay? See how long you can do this. What you'll notice is that setting up and tearing down the TCP connections can be done really fast, but then after a while, setting up a new TCP connection is actually going to take some time, 30 seconds to be precise, if I remember correctly. And this has everything to do with the so-called wait time in the TCP protocol that says I will really tear down my connection after a number of seconds have taken place. And this has everything to do with handling broken TCP connections across the internet. And basically it has to jump to a new part of the sequence number space. For those who think, whoa, this is going deep, check out the TCP protocol. Or, like I said, try to do this experimentally by just setting up a bunch of TCP connections until you can no longer set up TCP connections. Break them all down, and what you'll notice, you'll still fail to set up new TCP connections. It's also related to the number of file descriptors that you can that you get from your operating system. Okay. Okay, watch this. This is important. Servers and state. The concept is very important. I'm going to talk about stateful and stateless servers. And what I just wanted to say is, once upon a time, which is approximately 10 years ago, it was extremely important that you set up stateless servers. I will argue in just a minute that by now it is still important, but less important than 10 years ago. Okay? What is a stateless server? And now you got to start thinking along with me. A stateless server is a server that does not keep an accurate account of its clients. And there are many examples of this. You do not record whether a file has been opened. This is what you normally do in an operating system, right? If you want to access a file, you first open the file, you do your read and write operations, and then you close the file. Now what you need to realize is that opening a file is not a necessity. The opening of a file is a function that is provided to optimize the functioning of an operating system. Because what the operating system can do is load all kinds of data structures and instantiate them inside the operating system so that it is much more efficient later to do the read and write operations. And when you close a file, it essentially discards those data structures again. So it's really an optimization issue. Strictly speaking, it's not necessary. And when you open a file, the operating system will maintain state on that file, like where you are and all this kind of stuff. Okay? A stateless server will not do this. It may mimic the behavior of opening and closing a file, but strictly speaking, it will not do this. Another thing that you can do in a stateless server is basically you do not promise to invalidate any caches. Okay? So when I was talking about Globule one of the previous times, I said, well, a replication strategy could be, hey, I'm going to allow you to keep content that you just requested in a local cache, and then I will inform you when that content on my side is updated. I will send you a notification. But if you promise to do that, that means that you as a server will have to keep track of the fact that that server, that cache server over there, has your content. Okay? Because otherwise you shouldn't make these promises. Stateless servers don't make these promises. And in general, you do not keep track of your clients. And the consequences, these are important, are that clients and servers are completely independent. Well, almost. Almost, okay? This means that if either one actually crashes, who cares? If I'm a crashing server, a crash server, and I recover again, I don't have to remember anything. I didn't remember anything, so I can just start a brand new life. No harm done. Almost. Okay, but in principle, no harm done. That's the big advantage of having a stateless server. It doesn't know anything about you. Which means that if it crashes, recovers again, no harm done. Which also means that state inconsistencies due to client or server crashes are strongly reduced. Just imagine that you had a stateful server that pops up again, recovers from a crash, and now it has to ask itself, where was I? And what this means is that in order to answer that question, where was I, you will have to make sure that anything that it needs to know to successfully recover has been stored somewhere. Got it? Everything that you do has to be kept, let's say, on disk, such that when the server pops up again, it says, okay, let me fetch my state from disk and recover from that. That's called a checkpoint. And as you may imagine, checkpointing may or may not be a very expensive operation. We'll come to fault tolerance in Chapter 8, but this is the basic idea. Okay. And there may be a possible loss of performance. For example, in the case of file systems, if you know where a client is when it comes to reading or writing data blocks, you can anticipate that by already fetching blocks into main memory, okay, when it comes to reading a file. Does everybody know what a connection-oriented communication is? Like a TCP connection. Okay? And just to recap this, what you do in TCP is a connection-oriented communication facility. You set up a connection. Once you set up the connection, you start sending packets back and forth. Okay? And then you tear down the connection. And you set up the connection for a number of reasons. A very important one is that you, as an operating system, will reserve enough buffers so that you can do a decent retransmission when things go wrong. The crux of the matter is you maintain state on behalf of this TCP connection. Is this clear to everyone? So here we go. Can I build a stateless server on top of a TCP connection and still call it stateless? Let's first vote. And remember what I said. You guys are master students. You got to have an opinion. Okay? I don't care how well formed this opinion is, but you've come into a state of your studies that you can actually think and then say, I think it should be this. You know, and don't worry, you're more clever than you may actually think you are. Who says, yes, it makes sense to talk about a stateless server even when you're using TCP connections? Let's vote. Very good. Okay, how many say no? Impossible. Okay, I see some people say no. There are people in this room who did not express their opinion. I want to vote this again. Who says yes? Who says no? Okay, at least a bit more hands. Okay. Why do you say no? No?
Well, I think by keeping state with TCP protocol, I mean, it's already stateful, and whatever we have on top of it, we'll still have some state kept involved with the TCP. So the whole system won't be, the whole communication won't be stateless.
Okay. Shall I repeat this? I will repeat the crucial part of your answer. You're saying no, you cannot say it's stateless because the system as a whole maintains state because of the TCP connection. That is a correct answer. Okay. Did you say yes? Yes. You did. You don't say no again. Okay. Why did you say yes? Why did you say yes, it makes sense to talk about a stateless server on top of a TCP connection?
I think that if we can keep the state in the connection without storing it anywhere, we can call it a stateless.
Okay, I'll repeat your answer. I'll rephrase it a bit. You say if we can keep the state confined to the TCP connection, that means that the server does not have to maintain state. It's a stateless design. That answer is also correct. I think it's more correct than your answer. And my answer would be, yes, it does make sense to talk about a stateless server on top of the TCP connection because of the separation of concerns, which is basically what is in your answer. You're separating a communication service, which need not be stateless, like TCP, but on top of that, you're building a server that does not maintain state about what's happening on the client side. So you can have a stateless server on top of stateful connections. But I do buy your argument because you said the system as a whole is not stateless, which is correct. Okay? And in principle, you just gave the same answer as she just did. Okay? But I like your answer better. More important is that you understand the concepts of stateful versus stateless. Okay? So a stateful server does keep track of what's going on the client side. So you do record that a file has been opened. And you do know where your data is cached. And it turns out that in many cases, because a server actually does maintain state of its client, in general, it can offer better performance. Now, what you see nowadays is that we're moving a bit away from pure stateless servers to more stateful servers. And this has everything to do with the fact that we now do understand how you can actually build robust stateful servers. And by robust, I also mean that when they do crash, they actually can recover pretty quickly. We'll come back to these things later on, but there are all kinds of tricks that you can actually apply. This does not mean that stateless designs are are off. You know, they're still there. To give you a very good example, NFS, and we'll be discussing NFS towards the end. NFS used to be a fully stateless design. NFS is the network file system, a fully stateless design, exactly for the reasons I just mentioned, up until and including NFS version 3. And starting from NFS version 4, they actually switched to stateful servers for a very simple reason. They wanted to accommodate wide area networking. And to do that, what you need to do is to allow clients to actually cache data from a file. But that does mean that the server will need to keep track of where its files are, more notably at which clients they are. Now that's a stateful design. Okay? Yes. Let's take a look at a bit at server clusters. In essence, I already discussed this. Okay? If you zoom into a website, and a more serious website, you will see a distinction between something at the front. I used to call this the user interface when I was talking about the three-layered approach. You had a browser, you had a processing layer, and a data layer. In the case of a website, this top layer is actually your entry point into the website. And you could argue that it's actually a proxy for clients to this website. Now what happens in practice is that you have switches over here. So requests come in at a website, and the web server, often just an Apache web server, what it basically does is make sure that these requests are handed off to other servers. You can have an Apache web server for that. You can also have load balancers as offered by the Ciscos of this world, okay, which have a different functionality, but the core thing is they switch off, they take incoming requests, and the first thing they do is try to get rid of it. Later, they will get responses back, and then they will make sure that the response is actually pushed forward back to the original client. And I'll give an example of that in just a minute. Zooming in, you will discover application servers or compute servers. These beasts are things where people say the business logic is running. I always had a tremendous difficulty understanding what this business logic is. I'm used to C programs. I'm not used to logic. But basically it says these are the servers that are running your programs that do things. And what do? Well, they do compute things, for example, or they combine transactions, but in the end they operate on the third layer, which is a distributed database. Now the thing to realize is that you have this separation into three layers. The separation between these two need not be exactly the way that I sketched over here. There are essentially two types of implementations. You can actually have a distributed database that is accessed from the application servers. That's one. Okay, just really imagine this. This is a joint database, and these guys over here access that database by means of all kinds of communication facilities that we'll be discussing when I get to chapter 4. Another way that you can organize these things is that each of these databases is connected to one of these application servers. So then you have an application server with a data store, and logically that still means you have the separation between, let's say, a switch, application layer, and database layer. Do you see the distinction between the two? Is that clear to everyone? No. Okay. So the physical way of looking at this is the following. In the first setup, that is kind of represented in this figure over here, you have a distributed database. This distributed database appears to applications as really a separate entity. It is out there on the network. And you have software on your side that allows you to access that database through the network. How many databases you have, unclear. What the implementation is of that distributed database, unclear, except it's completely running on different servers. That's one implementation. Another implementation is that, no, the data layer has been implemented by means of the disks that are attached to your machine on which the application server is running. Okay? If you have K application servers, you have K database servers. One server, one database. The data is on the local disk. Okay? Logically, that still means you have this separation into 3 layers, but the implementation is fundamentally different.
So
yes?
If I understand the time of the request.
So let me repeat your remark. If you take a look at the difference when it comes to how to switch requests, the first configuration is that it really couldn't matter anywhere to which, in principle, to which application server you would forward a request, because every application server, in principle, has full access to the entire distributed database. It's just somewhere else, okay? The second type is that you now may need to take into account where data is physically stored, because you have to forward a request to that specific application server if you have a request for very specific data. Okay? And I'm considering whether I want to confuse you guys. Yeah, I'm going to tease you a bit. Because the first configuration can, of course, be implemented by distributing the data transparently across the same machines as where the application servers are running on. But the application servers don't know. Got it? Okay. I hope that adds up to the confusion, but think about this. And you see that, the distinction between the logical and the physical can be a thin one. Yes? So let me rephrase that. So is this similar to a NUMA architecture, a shared memory architecture, but you are unaware where exactly your memory modules are placed in the system. A NUMA is confined to a single machine. It could be confined to a single machine, but you have this distinction of being close or far away. But the interesting thing is it can be transparent, and that's the first one. The first architecture is in principle transparent to where the data is actually stored. Okay? And both types of configurations are actually used in practice. And in very large systems, there's a hybrid form. Okay. Now, let's focus a bit on the request handling. This is actually kind of important. Although variations on this theme actually occur. If you take a look at web servers, what you often do is you send a small request to a web server, and let's exaggerate a bit, you get a lot of data back. Okay? Now, if you don't watch out, if you have a client that's sending a request to a switch, and let me go back to the previous slide, to such a switch, and the flow is like this. Client issues a request, it enters a switch, is handed off to an application server, goes to a database, goes back and through the switch again. You could easily imagine that these guys over here have a lot of work to do. You can circumvent some of these problems by applying a technique called TCP handoff. And in TCP handoff, what you do is you let the client talk to a switch. The switch hands that TCP request off to a server, and the server responds back to the client. Now, you need to think along with me. How many of you recall the TCP three-way handshake? Okay. For whom of you is this totally blank? Okay. Maybe some of you don't dare to say this, but then let me briefly repeat this. In the three-way handshake, what you do to set up a TCP connection is that you start by sending a sync packet. I want to set up a connection. Okay? And there's the three-way handshake that basically tells, okay, I want to set up a connection. Sure, here are the sequence numbers that you need, and you acknowledge the sequence number that you're going to start with. From that moment on, client and server can talk to each other. Now, what you can do when you set up a TCP connection is the following. The client sets up a sync request to the switch. And what the switch does is select a server. And we're going to take a very simple policy. It just follows a round-robin approach. Okay? If it picked server 1 the last time, it's going to pick server 2 now. So what it does, it selects a server. It says, will you please handle this sync request? And then this server will send back to that client, okay, I'll agree to set up a connection. Here's the stuff that I want you to adhere to, sequence numbers and whatnot. After which, the client sends a request back, or actually acknowledges the setup of the request by sending, again, an ACK packet to the switch, which it will then have to hand off to exactly the same server it just selected after the communication can actually start. Yes. Does it mean that this server over here fakes the address of this switch? Yes, it will have to. It has to spoof that address because otherwise this client is going to be a bit confused, right?
Yeah.
Because what it does is really taking over a TCP connection, but not entirely, because the flow continues like this. Okay? Every request sent by the client, also read request, whatever, will flow through the switch, who will have remembered to which server it had handed off that specific TCP connection, handed off to the server, and the server will actually throw a lot of data back to you, like a full web page, for example. Exactly. Okay? But the beauty of this scheme is that you see small control packets flow through the switch to the server, and the big data transfer takes place from the server to the client. And the client really doesn't know. Yes? So if you want to turn things around, like your client is pushing a lot of data to the server, then this scheme is certainly not going to work. Okay? You will have a switch that's not going to be very happy. I am unaware of the techniques that are being used in that case. But I will show you in a minute an alternative technique of which variations do exist that actually could also handle that type of problem. Is this scheme clear? Yes? I'm sorry, I didn't get your question.
Doesn't this need many changes in order to work?
Whether this requires a lot of maintenance to work?
Many changes in the TCP, because this the way TCP goes.
Okay. I think I got your question. Let me rephrase this. Can you do this? Would you be able to do this by yourself? Let me phrase the question like this. I mean, if you would now go home and just, take your existing systems, can you actually implement TCP handoff? That's your, and the answer is no. Why not? Exactly. Socket interfaces do not allow you to do this. What you will need to do is modify the operating system, and specifically the implementation of TCP. You will have to modify the TCP stack to support this. Does that answer your question? Okay. Yes. Okay. If you would take this in terms of a three-layered approach, user interface, or what I just did over here, whoops, wrong direction. This one over here. No. No, I know. Way back when. Yes, way back when. Where you had this logical vertical layering application, where you have the application layer, data processing layer, and a user interface layer. Okay, let's take a look. Let's take a look at this question, this picture, and after this we'll have a break. I'm going to rephrase your question. Can you apply the TCP handoff to this scheme? And what you have to realize is, if I take a simplified view on Google, then Google implements a switch over here, has a bunch of application servers running all kinds of web services, for example, and it operates on distributed databases. Okay? Which is essentially what you're asking. What you're asking is, how do they know about each other? What will happen? So, tell me, what will happen?
I mean, people become the bottleneck that.
Oh, there will always be bottlenecks, but that's not the interesting issue. Can you apply TCP handoff to this setup over here? I cannot see why not.
It will only work if every application server has the same content.
Will only work if every application server has the same content, but that's because of the round robin selection.
But yeah, also because you hand off the request to a certain server before actually making a request to that server.
That is true. Yes, you hand off the request to a server before actually handling the request. That is true. So that means that the servers, the application servers, will really have to be the same. That's what I mean by the round robin. Round robin means I'm not going to take a look at what you do, application server. I'm just going to pick the next one, or maybe you have some load balancing information. But the fundamental question is, can you apply the TCP handoff to this scheme over here? The database system cannot access the client. Okay?
They don't have to. The application services don't have client.
And now I hear the database service doesn't have to access the client. This is interesting. Okay.
You have the compute service to do some computing, right? So they still have to do that, and they respond back.
And they have to, okay, the computing server still have to do something and they still respond back. This is interesting how you guys are thinking. Will you please separate things? And then you will find your own answer. Okay? This is just a setup. Okay? In this scheme, I'm talking about setting up a TCP connection. So if in this setup, this client, the client's request would lead to a TCP channel with one of these switches, there is no reason why that TCP connection cannot be handed off. Notice that the communication between, for example, a compute server and the database could also be handled through a TCP connection, but it can be a completely different one and has nothing to do with the client. And I think someone mentioned that. The database servers need not talk to the client. How would the application servers talk to each other? Which is possible. If you listen carefully, you know the answer. And if I would tease you now, hey, listen again by listening to the recording and see whether you can find the answer. Well, I'll give you the answer. The answer is you do that by means of separate TCP connections. Those TCP connections need not have to do anything with the TCP connection that the client is requesting to be set up. Oh, okay. Why do we... Okay, then for those who didn't get the part about, hey, can you apply the TCP handoff to this one? Listen to the recording, okay? Because the answer was really there. And the crux of the matter is separate TCP connections. What you need to do is think, how would you implement this? And it's not a single TCP connection that is flowing through an entire website. There are many of these. Or maybe it's TCP with UDP, UDP internally, okay? Take into account it's the client that sets up a TCP connection. Okay. Your question, why do you need to modify the TCP stack? Because this guy over here has to pick up a different IP address than it's really running on. Assumption that I'm making, this is really running on a different machine than the switch. Okay? So this guy has an IP address over here. This guy has an IP address over here. Normally what you would do is pick up your own IP address. That's when the client would get confused. Instead, what you need to make sure, let me first finish my sentence. You need to make sure that that server actually picks up the address that belongs to this switch. And why was I hesitating? I cannot preclude that there are actually control interfaces to TCP that allow you to do exactly that. Okay, I think this probably answers your question. What it does boil down to, that if you would have a standard implementation that's not going to save the day, you would at least have to have an interface at the socket level that will allow you to set a different IP address. If you have that, then you don't need to modify the operating system. Does that answer your question? Let me phrase it like this. I cannot exclude that such implementations exist.
I think that.
And if that's the case, then there's no need to separately modify the operating system. Very interestingly, The modification has already been made for you in the following sense. A mechanism has been offered to you that allows you to implement a handoff policy. And then you can go home and do it. But you see the separation between policy and mechanism. Thank you very much for your remark.